What's up, guys? My name's Michael and welcome to my YouTube channel. If you're new here, please hit the subscribe button and then hit the like button if you enjoy watching this video. So today, this series is about going through algorithms and data structures, and today we're going to talk about trees. So what exactly are trees? Well, it's like a linked list except you have left and right nodes. And let's talk about general trees, like trees definitions, properties, trees, tree functions, C++, tree interface, linked list structures for general trees, tree traversal, which is like postorder, preorder, binary trees, and yeah. So what is a tree? Well, a tree is basically a tree. It's like a data structure that looks like a tree. All right. Tree structures are indeed a breakthrough through data organization. They allow us to implement a host of algorithms much faster when using linear data structures such as lists, vectors, and sequences. Trees also provide a natural organization for data, and consequently have become ubiquitous structures in file systems, graphical user interfaces, databases, websites, and other computer systems. It's not always clear what productivity experts mean by nonlinear thinking, but when we say that trees are nonlinear, we are referring to an organizational relationship that is richer than the simple before and after relationships between objects and sequences. The relationships in a tree are hierarchical, with some objects being above and some below others. Actually, the main terminology for tree data structures comes from the family trees, with the terms parent, child, ancestor, descendant being the most common words to describe relationships. So it's like having a parent, a child, and descendants. That's what trees are. So a tree is an abstract data type that stores elements hierarchically, with the exception of the top element. Each element of a tree has a parent and has more children elements. Tree is usually visualized by placing elements inside ovals and rectangles, and by drawing the connections between parents and child with straight lines. We typically call the top element the root of the tree, but it is given the highest element, with the other elements being connected below. As you can see this. A tree with 17 nodes represents the organizational structure of a fictitious corporation. Electronics is stored at the roots. The children of the root store, R&D, sales, purchasing, and manufacturing are all the children of this tree. All right. Formal definition of a tree. We define a tree to be a set of nodes stored in elements in a parent-child relationship. If T is empty, which let's say T is a tree, it has a special node called a root, and that has no parent. So yeah, the root, we call it, is the topmost node. That's what we're calling it, the topmost node. That's basically the root. Each node of T differs from the root, and it has a unique parent. According to every parent, it has a child, right? Except the root. So the parent has children, and these children have more children, and these children have more children. That's what trees are. Note that according to a definition, a tree can be empty, meaning that it doesn't have any nodes. The convention also allows us to define a tree recursively, such that a tree T is either empty or consists of a root node R called the root of T, and quite possibly the set of trees whose roots are the children of R. Two nodes that are children of the same parent are siblings. A node V is external if V has no children. Okay, so node is external if it has no children, and two nodes of the same parent are siblings. So these are all siblings, right? This is an external because it has no children, right here, grades. A node V is internal if it has one or more children. So this homeworks and programs have one or more children, has homework 1, homework 2, homework 3. So that's why it's internal. Most operating systems files are organized into nested directories called folders, which each represent the user form of a tree. More specifically, the internal node of the tree are associated with the directories. External nodes are associated with regular files. In Unix and Linux, the root of the tree is approximately called the root directory, represented by the / symbol. Node U is an ancestor of a U if U is equal to V, or U is an ancestor of the parent of V. Conversely, we say that node V is a descendant of a node if U is a ancestor of V. Okay, so these are ancestors. If it's a descendant, if it's an ancestor of this. So yeah, that's what I mean. For example, the CS252 is an ancestor of papers. So it's an ancestor of papers, right? Because papers is a descendant of CS252. It's like all the way of its children, right? CS52 is a ancestor of parent papers, right? PR3 is a descendant of PR3. Where's PR3? I can't find it. Yeah, PR3 is a descendant of CS1016. Yeah, so this is a descendant of it. Subtree of a root. T is rooted at a node V in a tree consisting of all the descendants of V and T, including V itself. The subtree rooted at OS16 consists of these nodes. Okay. Edges and paths in tree. Okay, so an edge of a tree is a pair of nodes such that U is a parent of V, right? So this is like an edge of a tree because there's a node of U, book is a parent of preface, right? This edge. A path of T is a sequence of nodes such that any two consecutive nodes in the sequence form an edge. So in the other tree, here's a path: CS252 projects, demo, and market. So CS252 projects and demo, market. This is a path because you're going down the tree. That's what a path is. When using single inheritance, the inheritance relationship between classes in a C++ program programs a tree. The base class is the root of the tree. Okay, ordered trees. A tree is ordered if there is a linear ordering defined for the children of each node. That is, we can identify children of a node as being the first, second, third, and so on. Such an ordering is determined by how the tree is to be used. It is usually indicated by drawing the tree with siblings arranged from left to right, corresponding to their linear relationship. Ordered trees typically indicate the linear order relationship existing between siblings by listing them in a sequence or iterator in the correct order. A structural document such as a book is hierarchically organized as a tree whose internal nodes are chapters, sections, and subsections, and whose external nodes are paragraphs, tables, figures, bibliographies, and so on. The root of the tree corresponds to the book itself. We could, in fact, consider expanding the tree further to show paragraphs consisting of sentences, sentences consisting of words, words consisting of books. Characters. In any case, a tree is an example of an ordered tree and is well-defined ordering among the children of each node. Okay, so here, this is an ordered tree. Yeah, because it has descendants and stuff like that. Because there's a linear ordering defined for the children of each node. That's the reason why. There's a first, second, third. There's an order, like 1, 5, 6, 9. This is an ordered tree because it's ordered. There's a linear order. Let's talk about tree functions. The tree ADT stores elements at the nodes of the tree. Because trees are internal aspects of our implementation, we do not allow access to them directly. Instead, each node of the tree is associated with a position, which provides public access to nodes. In this reason, we discuss the public interfaces of functions of our ADT. We use the notation P rather than V to clarify that the argument to the function is a position and not a node. But given the tight connection between these two objects, we often blur the distinction between them and use the terms position and node interchangeably for trees. As we did with positions for lists in Chapter 6, we exploit C++ ability to overload the dereference operator to access the elements with a position. Given a position variable P, the associated element is accessed by $P. This can be used for both reading and modifying the element's value. It is useful to store collections of positions. For example, the children of a node in a tree can be presented to the user as a list. We define a position list to be lists whose elements are tree positions. Okay, so a position list is a list of whose elements are tree positions, and that's basically what it is. So this whole thing was talking about how you could have position objects. Each node is associated with a position object, which provides access to nodes, and that lets you have the position of the tree. The real power of a tree position arises from its ability to access the neighboring elements. So given a position P of a tree, we define the following. P.parent is return the parent. Error occurs if P is the root. P.children returns the position listed containing the children of node P. P.isRoot returns true if the P is a root, false otherwise. P.external returns true if P is external and false otherwise. If a tree T is ordered, then the list provided by P.children provide access to the children of P in order. If P is an external node, the P.children returns an empty list. If we wanted, we could also provide a function p dot is internal, which would simply return the complement of p dot is external. The tree itself provides the following functions. First two, size and empty, are just the standard functions that we defined for the other container we already saw. The function root yields the position of the root, and positions produces the list containing all the tree nodes. Okay, so size returns the number of nodes in a tree. Empty returns true if the tree is empty and false otherwise. Root returns a position for the tree's root. An error occurs if the tree is empty. Positions return a position list of all the nodes of the tree. We have not defined any specialized update functions for a tree here. Instead, we prefer to describe different tree update functions in conjunction with specific applications of trees in subsequent chapters. In fact, we can imagine several other types of tree update operations beyond the book. Okay, so this is the tree interface. We provide a interface for all the methods of a tree. We begin by presenting an informal interface for the class position. So what does a position have? It has a parent. Position parent, which is gets the parent. So we have a class position, and we have a parent that has a position, which is gets the parent of the current position. We have the children that gets the node's children. I'm guessing this is a list. Yeah, it's a list that it returns. Position list is root returns if it's a root. Is external, checks if it's an external node. Okay, so an informal interface that was an informal interface for position in the tree. We have provided a version of the dereferencing operator that returns a standard readable and writable reference. So specifically, we did not provide a version that returns a constant reference, but this would be an easy addition. Next, in the code fragment 7.2, we present our informal C++ interface for a tree to keep the interface as simple as possible. We ignore error processing, hence we do not declare any exceptions to be thrown. Here is the tree. We have position list, okay? We have size. Okay, so this is a tree. A tree has a given position, the node's position, and a list of positions. It's very strange. Wait, no. Wait, what? It's very strange, whatever. It has a size, it checks if the tree is empty, and it returns the root and gets all the nodes. Okay. Although we have not fully defined an interface for the position list, we may assume that it satisfies the standard list, ADT, as in Chapter 6. In our code examples, we assume that the position list is implemented as an STL of the objects of type position, or more concretely, list position. In particular, we assume that position list provides an iterator type, which we simply call iterator in our later examples. A linked structure for general trees. So a natural way to realize a tree T is a linked structure where we represent each node of a position with the following fields: a reference to the node's element, a link to the node's parent, and some kind of collection, or right to store the links to the children. If P is a root of T, then the parent of the field of P is null. Also, we store a reference to the root of T and the number of nodes in T in internal variables. This structure is schematically illustrated here. So we have a list that tells you the okay, wait. So we have a list that represents a list that represents the links to the children's nodes. Okay, that's what it represents. If P is a root of T, then the parent P is null, and we stored a reference to the root of T. Okay, yeah. Okay, so that's basically what it is. We have a link structure which we represent each node by. We have a list that stores the links of the node's children. So here's here's a node, and I'm guessing these are the children, and they have a list. So here's an element, it has a parent, but then it has a link to a list of children container that contains all the lists of the children's, and these are all the lists of the children for this element. Here's a link that has it, right? These all point to it. Yeah, and this points to the link of the list of all children, and my computer's about to die. Yeah, so this is illustrated here. Okay, so here is how they summarize the performance by implementing the tree. The analysis on the left is an exercise, but we note that by using a container to store the children of each node, we can implement the children P by using the iterator for the container to enumerate its elements. So if isRoot is external parent, children P, size, empty, root, positions, the running time of the functions of an n-node linked list tree structure. Let CP denote the number of children of a node P. The usage is O of n. So is root external? Yeah, that's just O of 1. The reason why it's O of 1 is constant time. The reason why it's constant time is because you want it to be constant. No, you don't want it to be. It's constant time because it's just checking if it's the root or not. So you don't have to loop through anything. That's why it's constant time. O of 1, the parent, that just returns the parent of the node. That's why it's constant time. You're not checking anything. Not really checking any if you're not looping through the list or anything. Children P, this is O of CP. I'm guessing, I don't know what that means. Whatever. Size and empty is O of 1. Root is O of 1. Yeah, these are just returning it, so that's why it's constant time. Positions is O of n because if you want to go through your position, you have to loop through it. And let's talk about tree traversal algorithms. And I'm going to go get a drink of water because my throat is hurting. So as with any tree of algorithm or anything, well, you need to go through it, right? Like, just as, like, looping through a list, array list, or what was the other one we did? A vector, and, wait. No, not array list. The, vector and, a stack and a queue and a DQ, right? You also want to loop through a tree, right? So how would you loop through a tree? Well, first of all, you got to know how the height of a tree and the depth. Because if you don't know the height of the tree, how can you know how far you're looping, right? Because the height of the tree is from the top to the bottom. What is the height? It's the height of the tree of the top to the bottom. From here down to here. Well, let's think about it. How do I get from here down to here? Well, let's look at it. Let's talk about it. Let's talk about it. So let's say P is a node of a tree, T. The depth of it is the number of ancestors, including P itself. So the node storing international has depth of 2. In this figure, let's go back. Where's the node of international? Where is it? Where is the node international? Okay, what was it? Where was it? Figured 7.2. 7.2. 7.2. 7.2. Trying to find it. The node storing international. See figure 7.2. Oh, right here. So the node storing international here has a depth of, what did they say, 2? I don't think so. I don't agree with that because there are 3 nodes. Node storing international has a depth of 2. Wait, why? The depth is the number of ancestors of P, excluding the P itself, the number of ancestors. I don't agree with that, but note that this definition implies the depth of the root of T is 0. Okay? That makes sense? Because you're not including the first one. Note that this definition implies the depth of T is, okay, the depth of P's node can be recursively defined as, if P is a root, then the depth of P is 0. Otherwise, the depth of P is 1 plus the depth of the parent P. Okay, so they're defining depth as how far you are from the top. So international has a depth of 2 because you're going from 1 to, it's that's the number, how far you are from the top. So that's why they define depth as having 2. Okay, so you could define the depth as if it's a root, then the depth of P is 0. Otherwise, the depth of P is 1 plus the depth of the parent of P. So here, the recursive depth T P, shown in the code below, computes the depth of a node referenced by a position P of T by calling itself recursively on the parent of P, adding 1 to the value returned. So here is they're basically checking if it's a root. If it is a root, which is the top node, then they return 0. Otherwise, they add 1 plus the depth of T.P.parent. So I'm not sure how they're defining parent. Oh, okay, I know what they're saying. Okay. So let's say in this example, you want to find the depth of programs, right? So the depth of programs, how far it's from the root, it's 2, right? 1, 2. So they define it as, okay, I'm going to keep going up, right? So I'm going to call depths of the first, I'm going to keep going up. Which is this? Is this the root? No, I'm going to keep going up. Okay, this is the root now, right? I'm going to return 0. So that comes back here. Now, I'm going to do 1 plus the depth of it, right? So then this would have the depth of 1. Then that returns it, and then this would have 1 plus that, which has the depth of 2. So let me go over it again. So basically how they're saying is that given this tree, if I want to find the depth of this tree, how far it is, I check if it's a root. If it's not a root, I'm going to add 1 plus the parent, the depth of the parent. Well, so this is not the root, so I'm going to do 1 plus the depth of the parent. What is the depth of the parent? Well, the depth of the parent, I don't know what it is. It's not the root, right? So I'm going to do 1 plus the depth of the parent. What is that? Well, this is the root now, so I'm going to return 0. So once I got here, the depth, I have 1, the value 1. Now I return that, now I have the value of 2, the depth of 2. That's what they're talking about. Yeah. Let's see. So that's what this code does. Simple implement C++ implementation is shown below. If it's the root, return 0. Otherwise, return 1 plus the depth of T and parent. The running time of the node is O of dp, where dp denotes the depth of the node P in the tree T, because the algorithm performs a constant time recursive step for each ancestor of P. Thus, in the worst case, the depth algorithm runs in O of n, where n is the total number of nodes in this tree T. Since some nodes may have this depth in T, although such a running time is a function of the input size, it is more accurate to characterize the running time in terms of the parameter dp, since it is often smaller than n. Okay, the height of a node in a tree T is defined recursively. If P is external, then the height of P is 0. Otherwise, the height is 1 plus the maximum height of the children of P. So the height of a tree T is the height of the root of T. For example, the tree of the figure 7.2 has a height of 4. In addition, height can be viewed as follows. The height is equal to the maximum depth of its external nodes. Okay, yeah. That makes sense. Because you're trying to find the height of the tree is the maximum depth of all the nodes, which is all the way down here. So the height of it was going to be here. It's how far from the bottom it is to the root. So 1, 2, 3, 4. So that's what the height is. So how do you find the height? Well, basically you have to go through all the nodes of the tree and invoke the depth function to compute the depth of each node. So we have the height, h equals 0. Then you're gonna loop through all the elements of the positions, all the positions, and then check if it's external. If it's external, then you set the h to equal the maximum of the height of h, maximum depth for every single one, and then you return it. So here's how they implement it here. Here the implementation of the algorithm is shown below. We assume that iterator is an iterator class for position list. Given such an iterator queue, we can access the associated positions as star q. So here we have int height 1, and we have int h equals 0. So we get all the nodes, the positions of every single node, like a list of all the nodes, right? Then we loop through all of them, and then we're going to basically check if each of them is external. If it is, then we get the maximum height for each one, and then we return it. Unfortunately, the algorithm height 1 is not very efficient, since height 1 calls algorithm depth on each node. The running time of it is then ON plus the summation of 1 plus dp, which is the number of nodes of t. dp is the depth of the node p, and e is the set of external nodes of t. In the worst case, the sum of 1 plus dp is proportional to n squared. Okay, so here is a better way to do it. It's called height 2. It's a more efficient manner by calling the recursion of definition of height. So if it's external, then we return 0. Otherwise, we start h equals 0, and we're going to loop through every single children. And we set h equal to the maximum of every single children. Otherwise, we return 1 plus h. Okay? More efficient algorithm, compute the height of tree for that node. So check if it's external, return 0 into h equals 0. Create a height variable, loop through all the children, get the maximum height, and then return it. It's more efficient because the algorithm is recursive, and it is initially called the root of t. It will eventually be called on each root of each node of t. Thus, we can determine the running time of this algorithm by summing over all the nodes and the amount of time spent at each node. Processing each node in the children p takes O of cp time, where cp denotes the number of children of node p. Also, the while loop iterates. Each iteration of the loop takes O of 1 time plus the time for the recursive call on a children of p. Thus, the algorithm h height 2 spends 1 plus cp time. So let's see then the summation. Okay, this is just a proof of it. All right, let's talk about tree traversals. Tree traversals, yeah. So there's a traversal is just a basic way of visiting all the nodes. You could do this easily. It's basically a basic traversal scheme for trees called a simple way is called the preorder traversal. And you could, another way you could do is a postorder traversal. So in preorder traversal of a tree, the root of t is visited first, and then the subtrees rooted at its children are traversed recursively. If the tree is ordered, then the subtree are traversed according to the order of the children. The specific action could, the specific action associated with the visit of a node depends on the application of traversal, and could involve anything from incrementing a counter to performing some complex computation for this node. The pseudocode for a preorder traversal of the subtree rooted at a node referenced by position p is referenced here below, so we could invoke this by calling preorder. So how do preorder work? Perform a visit action for a node p. For every children of it, recursively traverse the subtree by calling preorder. So here's how it works. The preorder traversal is used for producing a linear ordering of nodes of a tree where the parents must always come before the children in the order. So such ordering have different applications, but we explore a simple way of an application in the next round. So here what you would do, you would visit the node of p, perform the visit action for a node of p, go through the children of it, and then recursively go through its children. So then we go to its children. Okay, they have no children. Then we go to the next one, right? Because there's a list of all the children's. Go through each of its children. Well, there's no children, so we go to this one. Well, this has children, so go here, and then go to its children also. Okay, and then now we're going to go its children as well. And then we recursively go back up here, and then we go down and down. Come back up here, go through its children, then come back up. Yeah, that's what it is. So yeah. The preorder traversal of the tree associated with a document examines the entire document sequentially from beginning to end. If the external nodes are removed before the traversal, then the traversal examines the table of contents of the document. Preorder traversal is also an efficient way to access all the nodes of a tree. To justify this, let us continue the running time of the preorder traversal of a tree T with nodes N under the assumption that visiting a node takes O of 1. Okay, the height is similar to that of algorithm height 2. At each node P, the non-recursive part of the preorder traversal algorithm requires time O of 1 plus CP, where CP is the number of nodes of P. Thus, by proposition 7.5, the overall running time of preorder traversal is O of N. Preorder TP implemented in C++ performs a preorder traversal of the nodes of P. That is, it performs the preorder traversal of the subtree rooted at P and prints the elements stored at a node when the tree node is visited. Recall that for an ordered tree, the T.children returns an iterator that accesses the children of P in order. We assume that the iterator is the iterator type. Okay. Too much talking. Okay. That's just basically saying we go through every children, right? So we get a list of the children, go through every of them, go to its children. That's all it's saying, okay? Enough of this talking. Go to, for every children we see, or all these children, right? We're going to go to it, and then we'll go to its children. That's all it's saying, okay? So here, go to all these children, right? Go to its children. It has none. Okay, go to its children. It has none. So we'll go to the next one. Go to its children. Okay, it has one. Go to its children. Well, there's no children here. Sorry, so it goes to the next one. Go to its children. Okay, there's no children. Okay, so now we're done with here. Go to the next children. Okay, go to its children. Oh, it's done. Okay, go to its children. Okay, go to its children. Okay, now we're done with this. So now we have to go to the right because this is the the next children, right? It was the next of the paper's children. So yeah, that's what it is. Okay, too much talking. Okay, there's an interesting variation of the preorder that okay. You could get a string representation by adding them all up. Oh yeah, you can. That's just to print it out. You could add up all the trees. That's what it is. Technically speaking, implementation of various prints the first. Okay, so this is just printing it. It's just printing every single children. That's what it's doing. So before it goes through it, prints out the parentheses. Then you print out another. You go through it. Recursively call go through its children. So then it does parentheses. It does a comma, and then prints out parentheses. That's all this is doing. Okay. Let's talk about Postorder. Okay. So what is Postorder traversal? Another important thing is called Postorder. Okay, I'm getting a drink. What's up, guys? Okay, so I just got a drink of water, and now we're talking about Postorder traversal. So another important thing about tree or algorithm is Postorder. Order. This algorithm can be viewed as the opposite of preorder because it recursively traces the subtrees rooted at the children first and then visits to the root. Okay, so it goes to subtrees at the children of the root first and then visits the root. So it is similar to preorder, but that we use it to solve a particular problem by specializing an action associated with the visit of the node P. Still, as with the preorder traversal, if the tree is ordered, we make recursive calls for the children of a node P according to the specified order. Pseudocode for the Postorders visit here. So what do? They go through every children of P, then recursively traverse the subroot rooted at P by calling the Postorder, and then visits every action for the node. Okay, so that's just the. So they're visiting every children first, and then visiting the node. It's not the same thing as preorder, because in preorder you visited the node and then you visited its children. This is visiting the children first and then visiting the node. That's the only difference. The name of a Postorder comes from the fact that the traversal method visits a node P after it has visited all other nodes in the tree. Okay, so this is what they do. They go here and they check if it has children. Well, it doesn't. Alright, then let's go to the next one. Check if it has children. Alright, it doesn't. Alright, so we'll go to the next of the children of paper, right? So paper has another children. Child called, I don't know what this symbol means, but okay. Then it checks if it has its children. Okay, then it goes to this. Does this have children? It doesn't. So then we'll go to here. Then we go to the next children of this one. Alright, then does this have children? No. So then we're going to go back up to the root now. So instead of going to the root first and then the children, it's going to the children first and then the root. So then we go here, then we go to the S2, check if it has children. It does. Then we go here, does this have children? No. So then we go here, then we check, okay, so it has children, it has 2.2 also. Does it have children? No. Then we go here, because this is the next child of S2, of whatever this thing is. 2.3, does it have children? No. Alright, so then we're done with all the children of S2. Now we're going to go back to go back to 2, S2, and then we check the root, and then we check the more of the children first, and then we check the root. That's what it is. So analysis of the time is that it is a running time of Postorder is analogous to that of the Preorder. Postorder, it takes O of n, either visiting each. No, it takes O of 1. Okay. Okay, this is just printing out the every children. So they get the list of the children, loop through all the list of the children, print out the recursively call this function again, but we're using the children every time now. Putting its children for the position. Then we print out a space, and then after each call, after each loop, because this loop goes through every children, right? So after each children, we print out the actual child. That's why we recursively call this first. Because yeah, Postorder is useful for solving problems where my fault. Let's see. Postorder is useful for problems where we want to compute each property for each node P in the tree, but computing that property requires that we have to compute the same property for all the children. Okay, so here's just a way that this could be used. It's like a file system, size of the directory, then the thing. They want to visit each file first and then visit the directory. So yeah, directory. When I say directory, I mean folder. They want to visit each file in the folder first, then visit each folder. That's what this Postorder is good. Let's see. It can be computed by adding the size of the P itself. Okay, that's just this computation can be done. Okay. So here's another algorithm called Diskspace, which is present in the code. It performs a Postorder traversal of the file system, printing the name in the disk space by the directory associated with each internal node of T. When called on the root of T, disk space runs in O of n time, where n is the number of nodes in the tree provided by auxiliary function. Okay. What does that mean? Okay, so here they're just printing out. Here they have an object called I'm guessing it has like it's called disk space that has like a name, and then the actual like summary of it, right, for each thing. So they loop through, check if it's external, right, first, and then if it's not external, so that means it's internal, and they get the list of the children, then they loop through it all, and then they print out the name and the summary. Okay. Just a review of what external and internal means. External is, let's just go back. Go back. Where is it? External. Okay. So external means is that, let me just keep finding the actual definition of it. A node is external if it has no children. Yeah, internal means it has one or more children. Okay. So it's just external. When it says it's not external, that means it has. Not external means it's internal, right? And that means it has children. So that checks if it has children or not. This checks if it has children or not. So it has children. Not external means it has children, and that's why we'll get the position of each children and then go through it. Okay. There's other kinds of traversals. Okay, so preorder is useful when we want to perform the action for a node and then the children. Postorder is useful if you want to perform the action of the children and then the node. Although preorder and postorder are common first, there are other traversals. We could traverse a tree so that we visit all the nodes at the depth D before we visit all the nodes of D+1. This is called breadth first search. Okay, which could be implemented using a queue, whereas a preorder and postorder uses a stack. Okay. In addition, binary trees, which we discussed next, support an additional method known as in order traversal. Okay, so that was all the trees. I want to talk about binary trees. So a binary tree just has two children, right? It's a tree that has two children, and it's an ordered tree in which every node has at most two children, right? So let me just draw it out. Maybe there's a whatever. I'll just draw it out for you guys. So the binary tree looks like this, right? It could have at most two children, but it could have 0 children, right? At most. So you can't have 3 children. You cannot have 3 children. The maximum you could have is 2 children. That's what a binary tree is. Okay, the maximum you could have is 2 children. I'm just going to be repeating that for you. Okay. So you can't have 3. You have to have. You could have 0. You could have no children. You have 1 child, and you could have 2 child. Okay. The maximum you could have is 2. Okay. That's what a binary tree. Binary 2. Okay. That's what it means. So this is a binary tree because that's the maximum you can have 2 children. Each child node is labeled as being a left and a right. Each left child precedes a right child in the ordering of the children of a node. Subtree is the nodes. Okay, wait. Okay. A subtree rooted at left is called the left subtree of root. Rooted at the right internal. Okay. That's just saying this is a subtree. Okay. Because it's rooted at the left. The left subtree. And this is the right subtree. Honestly, I don't even think it matters what you call it. A binary tree is proper if each node has either 0 or 2 children. Okay. So this is not proper because, well, actually it is. Because each node has 0 or 2 children. So this node has 2 children. This node has 2. And it has 0. What would be improper is if it has 1 children. Because they say, so like let's say I have this. Like that. Because then that means that, oh wait, I forgot the circle on the other one. See, now it has 1 children. It doesn't have 2. So that's why that's improper, right? Some people refer to such trees as full binary trees. Okay. So proper trees intern has 2 children, exactly 2 children. In a proper binary tree, every node has 2 children. Okay. Binary trees that is not proper is improper. Okay. So a different class of binary trees arises in context when we wish to present a number of different outcomes when we can result from answering a series of yes or no questions. So each node could be with the yes or no. Such binaries are decision trees because each call of external represents a decision on what you do. The answer leads to that. Oh, okay, so this is just an example. Decision tree, are you nervous? Save. No. Okay. That's just an example of it. Oh my god. Here's another example where they use binary trees for this. So let's say you want to do like on a calculator like 3 times 3 plus whatever. One way to do it to solve the numbers, like if I do like, I don't know, do 2 times 2 plus 5 or something. One way to do all these numbers, I did not put that correctly, but okay, whatever. One way to solve this is to use a binary tree. And how do these work? Basically, it's like the external nodes, which are the ones that have I forgot what was it. I think it was like no children. Yeah, the ones that have no children are associated with variables and constants. So the ones that have no children are the numbers here. So like these all have no children and they're the numbers. All these. Okay, so then each node and then the internal nodes are the ones with the plus minus multiplication divide operator. So all these are the internal nodes. Alright. So the node in each tree has a value associated with it. And if the node is external, then its value is that of the variable or constant. So these are external, so the value is the variable or the constant. If this node's internal, then you have to define it by applying its operation on the value of its children. So if it's internal, well, this is an internal node, so I gotta do 3 plus 1. Okay. And such an arithmetic tree is a proper binary tree since each of the operations must have 2 operands. So yeah, these are proper binary trees because each of them have exactly 2 operands. You might be thinking, well, what about this 3? This 3 must be, this has, it only has one of these, right? Well, that's not true because this 3 has no children, alright? And this X has 2 children. This 3 has no children, then that's fine. If it has 1 children, then that'll be something bad, really bad. Because that's not proper, alright? It's not proper if it has 1 children. You must have either 2 children or no children. See, the 3 has no children, 1 has no children. This has no children also. Alright. Yeah. So if you want to do this arithmetic expression, you put them all in the binary propers tree, and then you do this, like 3 plus 1, 2 times 3, do all these things. Alright. Value is labeled, that divides into 2. Okay, so a recursive binary tree definition. We could also define a binary tree in a recursive way such that a binary tree is either empty or consists of a node, R, which is called the root of T, and storing an element, a binary tree called left subtree and right subtree. Yeah, okay, so we know that, okay. Let's talk about binary tree ATDs. In this section, we introduce an abstract data type for a binary tree, as with our earlier tree ADT. Each node of the tree stores an element and is associated with a position, which provides public access to its nodes. By overloading the decrement, you could have the, dereference, my bad, dereference operator. With the position P, you could do star P to get the data that's stored at. Okay, so in addition, a position supports the following operation. So you could get the left child, an error occurs if it's an external. Okay, yeah, that makes sense. Error occurs if there's no children, so you can't do left child. Oh, whoops. Okay, yeah. Right child gets the right child. Error occurs if it's external. Parent returns a parent. P is a root, then an error occurs. Is root checks if it's root or not. External checks if it's an external and false or not. Tree itself provides the same operations as a standard tree ADT. Recall that a position list is a list of 3 positions. Size return the number of nodes in the tree. Empty returns true if the tree is empty and false otherwise. Root returns a position for the tree its root. An error occurs if the tree is empty. Positions returns a list of all positions. Okay. Alright, so these are all the functions. Let's talk about binary tree interface. The binary tree interface. Let me just check something. Okay. The binary tree interface. Well, so let's give a informal C++ interface for the binary tree. We begin the code fragment by presenting informal interface for the class position, which presents a position in the tree. It differs from the interface of the other one because we only have 2 children now. So we have left, we have right, we have the parent, we have the is root, returns with the root is tree as external. External means it has no children. Right, is an external. Yeah. Operator, star operator. Why don't they have like is internal? That would make more sense. That would just return true if it has children, instead of checking if it doesn't have children. That's just weird. But who am I to say? Alright, so here we present an informal C++ interface to keep this, and we ignore error processing. Okay, so now for the binary tree, list of the positions. This is just a list of the children, I think. Yeah, so the positions. We have the position node. Okay, we have size, empty, root. You have a list of the positions. Yeah, it's a list of the nodes. There's only 2 of them, so I don't know why they're doing it like this way, but it doesn't matter. Although we're not formally defining the interface of the class position list, we may assume that South is a standard list. Okay. You may assume that position list is implemented as an STL. Object position. Okay, properties of binary tree. So the set of all nodes of a tree is at the same depth. Yes, that makes sense because and it has the same level of D of T. Yeah, these two trees are at the same depth. That's what it just means. Like the set that the nodes of the tree. Level 2 has at most 4 children. Okay, yeah. D has at most 2 end nodes, yes. Okay, so the reason why it's 2 end nodes because you could multiply 2 every single time, maximum nodes. So, like, let's say I want... So the maximum depth here is, so 0, 1, 2, right? So this would be the, so if the maximum nodes you want is 1, 2, 3, 4, 5, 6, 7. Wait, what? 1, 2, 3, 4, 5, 6, 7. Okay. Yeah. The maximum you could have at level D is 2 to the 2 to the second. So 2 to the second. This is level 0, 1, 2, right? 2 to the second is 4. And these are the maximum nodes I could have at this level. At this level. Because it has 1, 2, 3, 4. That's what it means. We see that maximum nodes goes down the tree. We can derive the following properties of a binary tree as its number of nodes. Okay, so let's justify it as an exercise. Okay, so let T be a non-binary tree. N1, E1, H1. Number of external nodes. Okay. So, wow, this is just a mathematical property. Okay, the height plus 1 is less than or equal to n. What is n? Number of nodes. The height. Okay, so this has a height of 1, 2, 3. I guess. Or is it 2? I don't know. It depends on how you're counting it. 3 is less than... Okay, let's say it's 3, okay. 3 is less than the... less than or equal to n. Number of nodes. 1, 2, 3, 4, 5, 6, 7. Yeah, I guess that could make sense. It was less than or equal to 2 to the h, which is 2 to the third... H is 2, right? So 2 to the 2 plus 1 is 3. So 2 to the 3 is 4 times 2 is 8. 8 minus 1 is 7. Yeah. I guess that could make sense. What's NE? Number of external nodes. Okay, so that's the number of no children nodes. Okay, number of nodes have no children. There's 4 nodes that have no children right now at the bottom level. That's greater than or equal to 1, but it's less than or equal to 2 to the h. 2 to the h is the number of nodes in the diagram. H is less than or equal to an I, and 1 is the number of internal nodes. The number of internal nodes are the ones that have children. So 1, 2, 3. Yeah, 3. 1, 2, 3. Right, 3. Less than greater than or equal to h. H is 2, right? How are they defining h? Are they defining h as depth? Yeah, okay. 2 is less than or equal to 3. Which is less than or equal to 2 to the 4, which is 3 minus 1. 2 to the 4, 3 minus 1 is 3. Yeah, 3 is less than or equal to 3. I guess this works. Log n plus 1. I'm not proving this, okay? Oh, okay, they actually gave a definition how this works. No, they don't. They don't justify it. 1, 2h plus 1. 2h. 2 times h plus 1. Yeah, they don't justify this. Okay, the maximum nodes and the levels of binary tree in addition to the binary tree above. We also have the following relationship between the number of internal nodes and external nodes in the proper binary tree. Non-empty, the number of externals more than... Okay, I don't care. Okay. I don't think that matters. That's justification doesn't matter. Okay. Let's just skip that. Alright, a linked structure for binary tree. So in this section, we present implementation of binary tree as a linked structure. We present each node of T by a node object storing the associated element and pointers to the parent and two children. So like this. It has a pointer to the left and the right, and it has an element and a parent. We show the linked structure of the binary tree. So this would be the root of the tree. This is really complicated. Why is this null? So we show link structure. The structure shows the size, number of trees, and the pointer to the root. The rest of the structure consists of nodes linked together appropriately. If V is the root of the tree, then the pointer to the parent is null. Oh! Okay, so ignore this. This is the root, okay? The parent is null. Ignore this, okay? They're confusing me with this. They're just calling this the root, okay? It has a left. The left child is this, which is BWI. It has a right child, which is this. What's this pointing to? There's PVD, okay? Now, PVD has a parent, which is points to this. And then BWI has a parent and points to this, okay? Because this is a parent. Now it's the same thing for the structure down here. The left child points to this. ATL. ATL's parent points to BWI. JFK's parent points to BWI. BWI's right child points to JFK. So think of it, this is the left side, this is the right side, this is where it points to. The middle is the parent, where this is pointing to. That parent is pointing to that. This parent is pointing to that. Because BWI is the parent of these two child. That's why they're doing it. And then these are null because they don't have children. Right, that's why. We begin by defining a concept of binary series. The most basic entity is the structure node. Okay. So we have left, right, left parent, right element. Okay, we know that. Constructors initialize these to null. Okay. Each node has a. Okay, yeah, we know that parent, left, and right. We know that. Okay. Okay, now they define the position class. Its data members consist of a pointer V to a node of the tree. Access this node by overloading the dereference. Okay, we know that. So why did they? What's with this underscore? Okay, so the constructor initially initializes the node to have null pointer. The operator dereference, so you overload it. Okay, that just returns the element. So that left position, right position, parent position, is root, is external. Checks if it has no children. So does the left null and is it the right null? Yeah, that checks if it has no children. Because binary trees have two children on the left side and right side. So if you check if they're both null, then yeah. Then it has no children. Is external. Is external means it has no. Yeah, okay. So here's a position list of positions. Okay, the class and validity of the position list. It is nested in the public list. Okay. Let's go to the next one. Also the nodes is assembly invoking accessing appropriating members. Okay, I don't care. We have an included declaration. Okay. Is used to check in the collection. Okay, so yes, that's just saying they omitted error checking. Okay, so they omitted housekeeping functions. Okay. Okay, so here they have the functions for a linked binary tree. So they have size empty root. Root checks gets root. Okay. Position list returns a list of all nodes, which is literally 2. Okay. Add root. Adds root to the empty tree. Expand external. Okay, what does that mean? Expands the external node. I don't know what that means. Remove above external. So this removes. Okay, so expand external expands the external node. I'm guessing it. No, it doesn't return a position. Maybe it's printing all the things below it. I don't know. Remove above external. So that removes P and parent. Okay. Local preorder. Pointer to the nodes. Preorder traversal. Okay. That's what it's doing. Okay. Okay, so the private data contains a root nodes. Okay. And we have introduced a new. Okay, so they introduced the add root, expand external, and remove above external, which provide a way to build and modify trees. Preorder. Okay. Okay. So. Okay. So here's a constructor, and checks the tree empty, gets root. What the heck? Okay. We know these functions. We know these. Yeah, like adding a root to the empty tree just sets the root to the new, creates a new node, adds it, size 1. I'm more curious about expanding external. What do those mean? In addition to here's the class length list update function. The first is used to add nodes to the tree. The second is used to move nodes. Okay, so what does expand mean? Transform P from an external node into an internal node by creating 2 new nodes and making them left and right children of P. Error occurs if P is an internal node. So they create 2 new external nodes and make them the left and right children. That's what expand does. So if I want to expand, they didn't use expand. Why didn't they use expand? They didn't have an example for expand. The thing is, what do they put in the nodes though? The elements. I don't know. Let's look at the node. Remove above external. Removes the external node P together with its parent Q, replacing Q with the siblings of P. Error occurs if P is an internal node or P is a root. Okay, so they removes the above external node. So if this has no children, right, it removes W. And it removes the parent. And then it replaces Q with the sibling of P. So then Z becomes the node here. Wow, that's really confusing. That's what remove external does. Do you guys understand what they're doing? So they remove the one that has no children. So W has no children, right? It has no these square boxes. They don't have children with the square boxes, right? So they remove the external node, which is remove W, and they remove the parent V. Then they set the leftmost, the sibling of whatever was. So the sibling of W was Z. Set Z to have the new position of where it was. Okay, what about the expand? Do they have an example for? Okay, they don't even have an example of expand. The expand is shown in the code fragment below. No, it isn't. Okay. Okay, so expand means they change the external node, which is the one that has no children, and they add 2 new children to it, right? So here they created a new node. They set the left and right to have new children, right? And then they added it by 2. So they have a node pointer V points to the node, the position. Then they just allocate memory for 2 new nodes. Set the left and right parent and then add 2 to the number of nodes. But what do these nodes... These nodes have to have some data in it. The elements. Okay? Like, where's the data when you do dereference? That's what I'm curious about. Okay, we don't have replace. Okay, that doesn't matter. Here's here's how they implemented the remove the external. So they created a node that points to the parent, the current position. Then they create another node that points to its parent. Okay, if it's the child root, make the sibling the root. Otherwise, they get the grandparent, replace the parent by the sibling, remove, delete the 2 nodes. Wow, that's crazy. Okay, okay, so let's do it with their example. I'm gonna draw their example. What was their example? There's an example here. Somewhere down here. It was somewhere here. Yeah, right here. So let's see how they're doing it. Alright, I'm gonna draw their example. And then if their code actually works, we'll trace through their code together to just see how it's working. Okay, so they have a U, so this is a U node, Z box, another node. Okay, so we're gonna call remove external on W, which is this. Okay, let's see what it does. Let's trace over its code. So have W point to parents position.v. So W points to this position. So this is W. Okay. Node V points to W's parent. So this is node V. So this is a node V. We're gonna create a pointer to that. Check if W is equal to V dot left. So if W points to V's left, it doesn't. So sibling is gonna equal to V dot left. So sibling is gonna equal to this. This is sib. Oh, so this is just checking where the sibling is. Okay, if V is a root, it's not the root, because the root is up here. So it's not the root. No G pair is going to equal to V dot parent. So this is no G pair. G pair. It's going to equal to V dot parent, okay? If V is equal to G dot left, yet which it is, yeah, does V point to G dot left? G's left is this, right? V points to it, right? So we're gonna do this part. G left is gonna equal to sibling. So G's left is gonna now point to sibling. Okay. Wow. Okay. Then sibling's parent is going to point to this sibling's parent is going to point to G's parent. So this is sibling is going to point to that. Ooh, okay. I'm starting to get it. Delete W, delete V. Wait, delete W. So this is gone. Delete V. This is gone. Oh, so now this is gone. Oh, okay. I'm starting to get it now. Then you subtract 2 from the size. Then return the position. Oh, okay. So now this is going to become... like that now. Okay, I hope you guys followed my drawing. If you didn't, well, I'm not drawing it again. Sorry, no. That was that. Invokes the ability to pre-order. Okay, so this traverse is pre-order. Preorder traversal. How are they doing it? Positionless PL. Do a pre-order on the PL. Give the root. Return positionless PL. Okay, so we have a list of all the nodes. Call preorder of the root. Oh, okay. Oh, okay, that makes sense. Okay, so this is the preorder. So we're going to add it to the list, which is the list that we have, the current position. Okay. If left is null, is equal to not equal to null, then we go to left. If right is not equal to null, we go to the right. That's not that bad. I don't know why you have to push a position though. I'm guessing that's just to see if you gotten through the node or not. Okay, performance. Each position is O1 for is left, right, is parent, is external. Yeah, that makes sense because it depends on the machine. Size of node is O1, yeah. Accessor runs O1. Move external run O1, really? I guess that makes sense because they only changed it where it points to. Functions employ preorders over n. Yeah. Just functions of traversals over n. Okay, yeah, that makes sense. Yeah, we could talk about a way to make vector-based structure for binary. Alright guys, so let's talk about vector-based structure for binary trees. So a simple structure for representing a binary tree is based on a way of numbering the nodes of T. So now for every node of T, V of T, you can let f of V be the integer defined as follows. So if V is the root of T, then f of V is 1. If V is the left node, then f of V is 2 f of U. If V is the right node of U, f of V is 2 f of U plus 1. This is known as level numbering of the nodes in a binary tree because its nodes on each level is increasing order from left to right. Oh, that's cool. Wait. See, level numbering suggests a representation of a binary tree that mainly means a vector S, which is that node V of T is associated with the element S of rank. Okay. Simple and efficient. You could use it to perform functions left, right. So they're writing a mathematical function that allows you to get the nodes on left and right, I guess. So position is simply a wrapper for the index. Okay, so let n be the number of nodes. And the maximum value has size of f of m, which is the maximum value of f of v plus 1. For height of h, n is o equal to o of 2 to h. Yeah, we know that. Worst case is 2 to n minus 1. Justification. We discuss the heaps, which is n equal to n plus 1. This is why the worst case there's a still. Okay, so still for binary trees, the worst case. So, how are they doing this? I'm actually curious. How are they doing this? Do they give an example of how they're numbering it using a vector-based approach? Oh, okay. So, they're going to have a vector, which is this. It's pretty much like an array. We already talked about that. A vector of all these nodes, right? And then each node is going to represent, like 0 is going to represent the null of the parent, which is parent is null, right? 1 is going to represent the root. 2 is going to represent the left side, and then 3 is going to represent the right side. And you can represent all these by just going through the list and just having, for the next one, just represent each children. So 4 is going to represent the child of this x. 5 is going to represent the child of this, the red child of this x. 6 is going to represent the... Oh, well, 3 represents the child of that. Okay, so then 6 is going to represent... So they jump from 3 to 6. Okay, so 6 is going to represent the minus sign. 7 is going to represent the 2. And then here, 8 is going to represent the 3. 9 is going to represent 1. Okay, why did they skip 10 and 11? Oh, I'm guessing because there's no children for these, for 4. 10 and 11 is supposed to represent children for 4. And then 12 and 13 represents 9 and 5. Okay. Okay, so left, right, master 0, 1, size, empty, root, expand, positions. Okay, so now let's talk about the traversals of a binary tree. So pre-order traversal of a binary tree, we already talked about this. Go left and go. Okay, if it's an internal node, then go left and right, and recursively call pre-order on the left and right. Okay. So yeah, if it's post order, then you check if it's internal, then go call post order left and right, but then perform the visiting action afterwards, like whatever you want to do for the node afterwards. So rather than the pre-order that does it before, you go left and right, you do it after. That's post-order. Evaluating an arithmetic expression. So they're just going to go through the whole arithmetic expression that we saw before, and they're going to just do it. So if it's an internal node, they're going to evaluate x, the left side, that they're going to set that to x, and they set the value for the y to whatever is y, the right side. Then they do whatever the operator was associated it, and then they return that x, whatever operator y, and they return the value of it. The expression evaluation provides an O of n algorithm for evaluating an arithmetic expression represented by the binary tree with n nodes. So indeed, like the general post-order traversal, the post-order traversal for binary trees can be applied to other bottom-up evaluation problems. The specialization of the post-order traversal tree for binary trees simplifies that for general trees. However, because we use the left and right functions to avoid loop that iterates through the children of the internal node. Okay, so that's that. So now we have another traversal, which is called in-order traversal. So what is in order? Well, you go to the left, then you go to the node, then you're going to go to the right. That's what in order is. So an additional traversal for the binary tree is in order. In the traversal, they visit the node between each recursive left and then node, then they visit it to the right. So the in order traversal is, if it's an internal node, go to the left, then we visit the node, then we go to the right, and check if it's right, it's an internal node, then we visit the right. When I say internal, that means it has children. Okay. For example, in order traversal binary tree shown here visits the nodes. The in order traversal can be informally by visiting the nodes of T from left to right. So this is in order because we're going 3, then plus, then 1, then we did left, then we do times, which is in order, right, which is 3, then we do, because we did a left, that was this left, and then we got to do the node now, divide, then we got to do whatever's on the right side. Well, whatever on the right side, we got to do stuff on the left first. Well, there's still children, so I got to do stuff on the left, then we do the node, minus, then the right, then we do, that was the left, then we got to do the whatever's on the node, plus the node on the right, and then we take whatever our answer was on this left side, do the division, then the node on the right. That's basically what this whole in order traversal is. It's different because, so pre-ordered was you did the node first, you go to the node first, then you do left, right. Post-order, you did the left, right, and then you do you visit the node. In order is left, then node right. That's what it is. Okay, let S be a set whose elements have an order relationship. So for example, S could be the set of integers. Okay. Each internal node of P of T stores an element S known as X of P. For each internal node P of T, the elements stored in the left subtree of P are less than or equal to P of X of P. The elements stored in the right subtree of P are greater than or equal to X of P. External nodes of T do not store any element. Okay. An in-order traversal of the internal nodes of binary tree visits the elements in non-decreasing order. We can use the binary tree T to locate an element with a certain value X by traversing down, and then computing to search for our element. Okay, so that's the good thing about in order, because you're going through in order. So that allows you to search for nodes. That's all they're saying here. Note that the time for searching for the tree is proportional to the height. Okay, so the height has n nodes, then time could be as small as log of n, base 2 by the way, or as large as, was it theta? Was it omega n? Was that theta? No, omega n. Thus, binary trees are most efficient when they have small height. We illustrate the example search in the binary tree search in this. We study binary trees in more detail in the section. Okay, so binary tree stores this many integers. The blue solid path to traverse when we search for 36. So yeah, because we're going in order, we could search for whatever value we want. Okay, so Using in order for tree drawing. In order can be applied to the problem of computing a drawing of a binary tree. We could draw a binary tree T with an algorithm that assigns x and y coordinates to the node P of T. Following the rules, x of P is the number of nodes visited before P, and y of P is the depth of P. Okay? So they're going to count the depth and see how it correlates with the number of nodes. So how high it is and the number of nodes they're visiting. That's what this means. X of P is going to be the number of nodes and y. So you could take the convention computer graphics where as x increases from left to right, y increases from top to bottom. Okay? I mean, did they do any... Okay, whatever. They didn't really explain. Because this x is the... Okay, whatever. Euler tour. Tree informs of iterators. Yeah, each traversal visits the nodes in a certain order and is guaranteed to visit each node exactly once. We have unified the tree traversal algorithms given above into a single framework by relaxing the requirement for each node. Resulting traversal method is called the Euler tour. Okay. Advantages is that it allows for more kinds of algorithms to express easily. Euler tour is a walk around T. You go from the root toward its left child, viewing the edges of T as walks. And the edges being the wall. Oh no, the walls. Okay, the walls. That we can keep to our left. Each node is encountered 3 times by the Euler tour. On the left, before the Euler tour, P subtree. From below, between the Euler tours of 2 subtrees. On the right, after the Euler tours. Right, subtree. If P is external, then these visits actually happen at the same time. Oh, okay. So basically they're saying, okay, we're gonna start here. We're gonna go through all these things, right? All the tours. All right, traverse through everything. All right, and then we traverse to the right side. Traverse the node right. You go through these, and you go back. It's an Euler tour. Perform the action on the left. If it's then do the left subtree. Perform the action. Then if it's a node, recursively tour the right subtree. Okay, this is the same thing as in order. But they're considering the edges as tours or whatever. The preorder is equivalent to Euler tour traversal, in which each node occurs only if it is encountered on the left. Only when it is encountered on the left. Likewise, in order and postorder traversals binary are equivalent to the Euler tour. Yeah. Each node visit action occurs only when it is encountered from below or on the right. Euler tours traversals extends the preorder, in order, postorder traversals, but it can perform other kinds of traversals. For example, suppose we want to compute the number of descendants of each node P in an n-node binary tree T. Start an Euler tour by initializing a counter to 0 and then incrementing the counter each time we visit a node on the left. To determine the number of descendants of a node P, we compute the difference between the values of the counter when P is visited on the left and when it is visited on the right, and then add 1. Okay. It's counted, therefore we have an O of n time computing the number of descendants of each node. Or any time the Euler tour traversal is easy to analyze, assuming that visiting a node takes O of 1 time, namely, in each traversal we spend a constant amount of time at each node of the tree during the traversal, so the overall running time is O of n. Another expression of the Euler tour is to print a fully parameterized arithmetic expression. Arithmetic print expression shown in code fragment 7.29 accomplishes this task by performing the following actions. On the left, you print the left, then below the node. From below action, print the value or the operator, then print the right. If it's on the right action, print the other right parentheses. Okay, well this is just printing it in order. Yeah. Okay. Okay, so let's talk about the template function pattern. Tree traversal functions described above are actually examples of an interesting object-oriented software pattern called template function pattern. Does not be confused with template classes or functions. Principle is similar. Template pattern describes a generic computation mechanism that can be specialized for a particular application by redefining certain steps. Euler tour with the template function pattern. Following the template function pattern, we can design an algorithm template Euler that implements a generic Euler traversal of a binary tree. When called on a node P function, Euler calls several other auxiliary functions at different places. First, it creates a 3-element structure, stores the result of the computation, calling auxiliary function, init result. Next, if P is an external node, Euler calls auxiliary function visit external. And then it executes the following steps: calls auxiliary function visit left, performs a computation with node on left, recursively calls itself on the left visit left, calls auxiliary function visit below, recursively calls function on the right, calls auxiliary function visit right. I don't. What's the difference? Template Euler results the computation by calling auxiliary function return result. Okay, so it's like a template skeleton of an Euler tour. Okay, so you store a result in R. What is result here, though? I don't get it. If P is external, which means it has no children, then the result is the final result is equal to visit external. Otherwise, do the left side, get the result, visit below, do the right side. What the heck? Okay, when we do contains function template Euler contains all the auxiliary functions called by template Euler as an empty placeholder. Contains a function execute that calls template Euler root. Okay, okay. Template function examples. First, we're going to evaluate the expression associated with an arithmetic expression by writing a new class or a value expression that extends Euler overrides the array of 3 members, overrides visitor, visit external, overrides visit right. Okay, then you print the expression that extends Euler overrides the function visit external, printing the variable associated with the node, overrides the visit left, overrides printing the operator, overrides visiting right. C++ implementation. Left and right, final result. Okay, so I know what it is. Binary tree and position for the tree and position in the tree. What? In order to avoid typing lengthy qualified type names, we give 2 type definitions: binary tree and position for the tree, and a position for the tree. The only data member is a pointer to the binary tree. We provide a simple function called initialize that sets this pointer to a existing binary tree. Oh my god. What the hell? Okay. So now okay, what is going on? Left right result. I don't understand what they're trying to do here. Type definition position. Okay, store the tour results. Result from left, result from a combined result. Position in the tree, data member, pointer to tree, initialize local. What the hell? Principal traversal calls Okay, so it's up to derived functions to provide more interesting definitions of generic functions. Present a derived class as a value expression tour. Evaluates an integer arithmetic expression tree. We assume that each external node of an expression tree provides a function called value, which returns the value associated with this node. We assume that each internal node of an expression tree provides a function called operation, which performs the operation associated with a node to 2 operands left, right, and result. Okay, external, visit node, visit left, visit below, visit right. Okay, wow, I don't understand what they're trying to do here. Main point is to initialize the recursive or the tour, starting at the node and printing the final result. If you guys understand what's going on, like if you're reading this like you're reading, like how I'm reading it, tell me what's going on, because I don't know what's going on at this point. Okay? You print the final result. The final result is -13. Okay, so these are all generic types. What is going on? Binary tree, position, result, result. See out position tool, visit external, visit right. Visit external r dot final result is equal to the star p dot value. Visit right r dot result final result is star p dot operation left and right. Okay. Okay then. Now, finally, we present a derived class called print expression toward an expression to reevaluate the value of an expression tree. This one prints the expression. We assume that each node of an expression tree provides a function called print. For each external node, this function prints the value associated with this node. For each internal node, this function prints the operator. For example, printing plus and times for addition and multiplication. Okay? So they have execute that executes the tour, initialize t dot root, they print it out. Visit external prints the star p dot print, and it's virtual, so this is, people have to override this. Visit left is key out left. Visit below star p dot print. Visit right star right. Okay, I'm starting to not understand what's going on. By entering the subtree, the visit left has been overwritten to print the left, and on exiting the tree, the visit right has been overwritten to print the right. Main entry point is the function execute, which initializes the tree and invokes the recursive or tour. Starting at the root, when combined, these functions print the entire expression. Albeit the redundant parentheses. For example, given the expression this. Okay, so they're just evaluating the expression. Why don't they just do in order traversal? Why did they create a bunch of these classes? Maybe for generics? I don't know. Because templates? Why do they do that? I don't know. Okay. You can represent general trees with binary trees by transforming the tree to a binary tree. You could assume that either t is ordered or that is arbitrarily ordered. So for every node u of t is an internal node u prime of t prime that is associated with u. If u is an external node, that means it has does not have children, right? Does not have children, and it does not have siblings following it. Then the children of u prime in t prime are external nodes. If u is an external node of t, and v is the first child of u and t, then v prime is the left child of u prime and t. Node v has a sibling w immediately following it. Then w prime is the right child of v prime and t prime. Note that the external nodes of t prime are not associated with the nodes of t. Okay, wait. So how are they doing this? Okay, so they have this random tree. Yeah, how are they doing this? They took E, they moved it up. Then they took, no, they didn't. Okay, so they took E, they added a node, then they added two nodes. For C, they moved D to become the child of C. They added a new node for C for the left side. They took the G of D out on the left side of D after they added to the right side of C. They added two new nodes and they added a node here. Then on the right side of A, they added another node. Okay, so let me just read this again. I don't get why with all these U prime, U and whatever. For every node U of T, there is an internal node U prime associated with it. Yes. Okay. So for every node, there is a internal node. What is internal node? Internal node means it has children. Right? There is a node that has children, U prime of T prime. T prime is the new tree, okay? So T prime is a new tree. So For each node U of T, there is a new node in the new tree that is associated with it, okay? I'm just translating this BS. If U is an external node of T and does not have a sibling following it, so U is a external node, so that means it has no children, and it has no siblings following it. Okay, then the children of the new node that in the new tree are external nodes, so it has no children. So if there's no children, if a node in the old tree has no children, then the node in the new tree has no children. When you translate it, I guess. No. C has no children, but has children now. But does not have a sibling following it. Doesn't have a sibling following it. So like E and F has no siblings following it. But it's external, that means it has no... Okay, yeah, so external means it has no children, right? It has no sibling following, then the children of the new node are external. Oh, I get it. Okay, so if it has no children on the left side, the old tree has no children. That means on the right side in the new tree, what they're going to do is, because it has no children, then the children of the old nodes will be the ones that have no children. So the ones that had no children on the old tree are going to have children in the new tree. If you get what I'm saying. So like E and F, they now have children. They could have just said that. I'll get it. So G is now going to have children. And yeah. If U is an internal node, so that means it has children. And B is the first child of U. Then V prime is the left child of U prime. Okay, so if U is an internal child node of T, so B has children, right? B has children, and U is the first child, and V is the first child of U. So E is the first child, right? Then the new tree is B is now going to okay, then the new child, then the first child in the new tree, so E, first child in the new tree, is going to have the first child, so in the new tree, wait, hold up. In the new tree, it's going to be the left child. So that didn't change. Oh my gosh. Why do they write it like this? It's just saying that nothing changes for the left child for a node. Okay? So E and B for internal nodes, nothing changes. So here this is B, right? E was the left child of B, right? On the new tree, E is still going to be the left child of B. That's all they're saying. Oh my gosh. Okay, if node V has a sibling W following it, then W prime is the right child of V prime in the new tree. So if node V has a sibling W, immediately following it. Okay, so let's say B has a sibling C, right? B has a sibling C. Then on the new tree, C is going to be the right child of B. Oh, okay. So if B has a new tree, okay, this is getting really complicated. So the siblings of it is going to become the child on the right side. That's all it's saying. Okay. So B has a sibling C following it, right? On the new tree, it's going to be the right child. So B's the right child's that now. Okay. So E has a sibling F, right? E's right child is going to be F. That's what it's saying. Note that the external nodes are not associated with the interpretive mirror. Okay, okay. Woo! It is easy to maintain the correspondence with T and T prime is expressed in terms of T and T prime. And truly, we can think of its siblings. Corresponds in terms of conversation of T into T prime that takes each set of the siblings with parent V and replaces it with the chain of the right rule. Why? Okay, so they're saying... Okay, so this paragraph is basically saying that you could maintain the order of what's going on between your old tree and your new binary tree. Okay? So, okay, remember guys, this whole thing was about changing an old tree, right, to have become a binary tree. So what are they saying here? You could say the set of all the siblings, and to maintain the ordering, anything in the set of the siblings for all these things, for a parent, replace it with the chain of the right child root of it. So let's say these are all siblings. Replace the chain of the root to the right child of it to at V1. So C becomes the right child of B. D becomes the right child of C. Okay, that's what they're saying. All they're saying is that given a set of the siblings, whatever's on the right becomes the right child. That's all they're saying. If you want to maintain the order. This is pretty ridiculous. Okay, is that it? Whoa, that was it. Alright. If you guys enjoyed this video, hit the like button. If you're new here, hit the subscribe button. And that was all of the trees. I don't know if I'll do the exercises. I might do. I need to finish the other recursive exercises first. But yeah, rate, comment, subscribe. I'll check you guys later. Peace.